Cool, here we go. So part three, I guess, in unit three is all about chemical equilibrium. This is actually a pretty cool concept because, um, what you guys learned in chemistry, the first year chemistry is, or first unit of chemistry is actually not technically true. Chemical reactions don't always go in the forward direction. So with some reactions, the concentration of the reactants never actually reach zero. I just want to make sure I'm in the right spot. Yeah. So with some reactions, the concentration of these reactants will never reach zero. Products can react to make more reactants, and we call this a reversible reaction. So let me give you some examples. Cooking an egg or frying a chicken breast or making toast is not a reversible reaction. Once you cook the bread, you can't go backwards from that. When something, I hate using this example because it's not technically a chemical reaction, but a reaction that's reversible, you can think of making and melting ice. So freezing water and melting the ice back and forth, back and forth. You could do this tonight in your kitchen. Just take a glass of water, put it in your freezer, let it freeze, take it out, let it melt, put it back in the freezer, take it out, and on, and it will just always happen. You can just go back and forth forever. We call these reversible reactions, and we use a new arrow for that. Whoops, my PowerPoint's doing that thing again with the pen. Hold on, guys. Let me just restart my PowerPoint. Remember the issues I've been having with my pen? Let me just get out of this PowerPoint. Okay, just hold on, guys. Every time I download a PowerPoint from your D2L, I get some crazy issues with the pen, but I think I figured out how to get it to work. Okay, sorry, let's see. There we go. So instead of writing a chemical reaction like reactants go to products, some chemical reactions can be reversible or reversed. So we use what's called a double-headed arrow, or you might hear me call this an equilibrium arrow. All right. Now, again, not all reactions are like this. Again, cooking a chicken breast, frying an egg, even burning a candle, you can't really go back once you've done that reaction. But a lot of chemical reactions can go in both directions. And you're going to see this in your lab this week. It's a really easy and really cool lab. All right, so I don't know how well this is going to play for you, but this is a reaction that's reversible. So they used a bit of energy, some heat energy to turn it blue. And then once it cools down, sure, and somebody has their mic on, it'll turn back to clear and colorless. And you can go back and forth with this reaction all the time. Okay, so that's an example. The video is not very good, but you'll see this in the lab this week. So the definition of equilibrium is a reversible reaction where a very important definition here, guys, wink, wink, where the forward rate of reaction is equal to the reverse rate. And the reason I'm saying that's an important definition is a lot of students get that mixed up on an exam or a test or something where we ask you to multiple choice or define what equilibrium is. It's when the forward rate equals the reverse rate. Remember what we talked about in sections 1 and sections 2. Reaction rate is the speed of the reaction. So forward rate equal to reverse is the definition of equilibrium. All right, let me check the chat here. I got a couple messages. Oh, I am using a different mic. Okay. Yeah, sorry. I had my microphone unplugged this weekend. I was doing something online and I used another computer. So anyways, I got my old school mic back. There you go. Cool. Thanks for letting me know. So very important that you know that the
equilibrium is the forward rate equal to the reverse. They're happening at the same speed, so it's reached equilibrium. One kind of way to think about equilibrium is like if you bought a cup of coffee or something from Starbucks and you set it down on a table and just walked away. Eventually, that cup of coffee the temperature of it will equal the temperature of the room that it's in. We would call that thermal equilibrium, right? The coffee is not going to heat up your bedroom. What happens is your bedroom and the cup of coffee kind of meet at a certain place called equilibrium, where the heat getting put in and the heat escaping is equal. So that's called thermal equilibrium. And a chemical equilibrium is just when the forward rate and reverse rate are the same. So nothing is changing. And you'll see that in the lab this week. I kind of wish well, part of me wishes I could be there for your lab this week because it's definitely my favorite lab. I think you guys will like it. So here we go with the math, everybody's favorite. There's a number we can use to represent what's called the equilibrium constant for a reversible reaction. Okay, this is an easy calculation, but I want you to make sure you don't get this confused with rate. This is not, that didn't really make sense what I wrote, did it? This is not the same as rate. Okay. So what I usually tell my students in 1121 is you can think of chapter 3 being broken into two parts. Part 1, the first two sections, is about reaction rate. Part 2, the last two sections, is about equilibrium. And the reason I'm telling you this is because remember when we had the equation rate law? So it would be equal to K times the concentration of like your reactants. That is not the same K. And this is such a point of confusion for a lot of students. Like again, when you're doing this on a test, you're doing this on a final exam, think of chapter 3 as broken into two parts. If you hear the word rate, think of part 1, where we talked about rate laws and rate equations. If you hear the word equilibrium, or you see arrows like this, think of part 2. I don't know why in chemistry they decided to use K twice, but one thing I'll mention is that the rate K is lowercase and the equilibrium K is uppercase. Okay, I know that's confusing, but that's life. That's chemistry for you. We use the same symbols all the time. Okay, so the formula is the equilibrium constant, K, is equal to the concentration of the products over the concentration of the reactants. That might sound complicated, but I will show you how it works. The key for this is you can only calculate the concentration for an aqueous solution or a gas. Now, I want you to think about why that is. I noticed there's some stuff happening in the chat. I'll get to that in a minute. Concentration is moles of a chemical per volume, per liter of the container. Solids do not occupy the shape of their container, so we cannot calculate concentration of a solid. It's not something we ever did in chemistry. Concentration for a liquid doesn't really make sense because typically, again, concentration is moles per liter. So it would be liters of air or liters of water. It's a mixture and liquids are pure. So we can only use this equation for aqueous and gaseous systems. You cannot use this for solids and liquids. And I'm going to show you this. It's a lot easier than it looks. All right, let me check the chat. Yeah, well, as Aman says, yeah, don't they have another letter to represent? I don't know why. Well, I can tell you one thing. I don't know why the rate constant is K, but I can tell you that the equilibrium constant We are going to look at this in chapters 4 and 5. So very, very important. This K, this equilibrium constant, very important. We'll see it in Unit 4 and in Unit 5. It's amazing. Okay, how do we do this? So write the equilibrium constant equation for the following equilibrium. Well, the formula is always K is equal to the concentration of the products over the concentration of the reactants. Okay, it's always now. Some of you guys might be thinking, well, wait a minute. If this is an equilibrium, how do you have products over reactants? I mean, it's going forwards and backwards. What I mean is, no matter what, even if it's an equilibrium, we still consider the reactants to be on the left and the products to be on the right. That's just the rule for chemistry. We say products on the right, reactants on the left. So I notice that all of these chemicals are gases. You always omit, which means exclude, solids and liquids. Okay, so let's write this down. So concentration of my products, well, it's the concentration of NH3. There's my only product, divided by my concentration of my reactants, N2, sorry about my phone there, and H2. All right, there's one more thing. Well, no, there's two more things. I have so many students often get this part mixed up. These on the bottom are multiplied. Do not add. These would be multiplied. And there's one more thing. Unlike rate laws, these numbers do matter. These are not reaction orders. They have nothing to do with rate laws. So I will put my 2 here and my 3 here. You can see why you would get this confused with reaction rates. Do not confuse with reaction, or maybe not reaction rates, but rate laws. And what are some key differences between rate laws and equilibrium? Well, rate laws have a rate constant. Rate laws have reaction orders, which I have to give you. They would be in the question. Rate laws, we do not worry about products. Products have nothing to do with the rate law. Equilibrium, we do use products. There's no such thing as reaction order or rate constant, and these coefficients are actually used in the equation. All right, if you're all thoroughly confused, let's do another one. Let me do another one for you. Oh, there's one on the bottom. That's perfect. Okay, oh, I wrote too big. Are you guys okay if I erase the screen and try the one on the bottom? Is that cool for everybody? Did somebody maybe want to take a picture or something? This does go up on YouTube, guys, so you don't need to take any pictures. But I wrote way too big. All right, I'm going to clear my screen. Well, actually, I'll tell you what I'll do. I'll just write a little smaller here. So K equals concentration of NH3 over N2 times H2. And then I'll put my exponents in. So this is 2 and this was 3. And again, if you're wondering where those come from, they come from this 3 and this 2. Okay, let's do the next one. So in the next one, we have carbon solid reacting with oxygen. So this is the combustion of carbon and it forms CO2. Now there's something very interesting about this one. You cannot write the concentrations of solids. So never include solids or liquids? I know I mentioned it earlier, but think about it. What is the concentration of a solid? How does that work? The concentration of a solution is the moles of solute dissolved in water. The concentration of a gas is the moles of gas in a solution of air. But how would you calculate the concentration of like baking soda or, um, you know, concentration of like a diamond or a piece of iron? It doesn't make sense. So I write my products CO2 over my reactants, O2, and I'm done. Notice that I don't need to put any exponents in because they're all 1 and 1. So I'm finished. And I leave out the solid. We never include solids or liquids. All right, whew, cool. Now, there's some questions in the chat there, but what I want you guys to do, let me see the question first, but I'd like for you guys to practice this. Aman raises a good question. Do you need to mention the phase? No. If you do put the phase in there, that's not a problem. I would never take off marks for that, but you don't need to write the phase if you don't want to. So why don't you guys try some? You don't have to do all three, but I'm going to give you guys a couple of minutes to try these, and I will just give you a hint. Oops, sorry. Oh, my computer's being real slow. Hint. No solids or liquids, okay? It's always products over reactants. And that's it. I'm going to stop talking and give you guys a couple minutes to try this. If you could at least do 2 of the 3, that would be great. And I'll be back with the answers in 3 minutes, maybe 4 minutes. And then we'll kind of get to the mathy part of this, and then we're done. So I'll be back in 3 or 4 minutes. Take your time, and it's hard to type your answers in the chat, but you can try. All right, let's check it out. Let's see your answers. So, I mean, the way I look at this question is, I mean, once you practice a few of these, it's pretty easy. You just need some practice. And there are worksheets on this, by the way, with answers. The other thing I'll mention is, just be careful when you're doing this on a test, wink, wink, you will see this. There's 2 important things. One is really don't get this confused with rate law. When you see KC, oops, my pen, oh, this computer. When you see KC or the word equilibrium, or you see some of these arrows, immediately forget about the word rate law. Rate law, you're not going to see equilibrium. The other thing I'll mention is just watch out for those solids or liquids, right? So anything with an L or an S, get rid of it. Okay, we don't need them. You can't calculate the concentration for them. All right, I got a message in the chat, and then I'll go through. Yeah, okay, so Abdullah, you bring up a really good point. There's no numbers in these questions, and I'll just say to you, not yet. The next step, we might not finish this today, but the next step is putting numbers in these equations, and it's really easy. But yeah, all you have to do right now, Abdullah, and this goes for everybody, is put the product over the reactants. Easy. However, in the next part, I am going to give you numbers, and I'm going to tell you what these numbers mean. The numbers mean something really cool. Okay, so let's get our K's written now. I don't have a lot of room here, but I'll try my best. So the first one, ooh, my PowerPoint. Okay, let me try that again. I think I might need to restart my computer. And you'll notice I'm just writing K. You can put KC down if you want. K always represents the same thing. There's different Ks. There's Ka for acids. There's Kb for bases. There's Kc for concentration. There's Kp for pressure. There's so many different Ks out there. So if I forget to put the C down, don't worry. Okay, I'm sorry. I definitely need to restart my computer. Okay, anyways, here we go. Products. over reactants. And you'll notice I'm putting all of my products in and all of my reactants in because these are all gases. Okay, so that's the first one. Okay, what about B? B is the same thing. I got a pretty crazy chemical there, CCl2F2 times HCl squared. I apologize if you're looking on with your cell phone or something. And then HF squared. Again, guys, if you're wondering where these numbers come from, like why am I squaring things? Why am I putting a 3 or a 2 or something above a number? It is from the the balancing. And I remember last week we had a few questions. People were like, in a rate law, why aren't you putting in the coefficients? Well, in a rate law, the only thing that matters is the rate order, which is a number I give you. In these type of questions, we do use the coefficients. The other thing I'll mention is that if you were going to see a question like this on a test or a final exam, we do provide you with the balanced chemical equation. So you don't have to balance, you'll be getting stuff just like this. Now this last one is pretty cool. Everything got eliminated except the HCl. Okay, and that's it. Now you could put over 1 if you want to, you don't need to. I'll put it there for a minute. But you don't need to, you don't need to put the 1 there. All right, cool, that's it. That's not bad, is it, guys? How do you find that? I think the only issue with this, and again, I've taught this course probably 15 times. The only issue with this is that students, there's two things. They mix it up with rate law or they add these things together. Do not add. These are all multiply and divide. And the other thing is people get confused with rate law, and that's really the only problems people have with this. Oops. I'm going to check the chat. It's currently easy. Thank you, Yasmin. And Abdullah and Yasmin, you're saying currently it is easy. We're only going to take this up 1 level. And what I mean by take it up 1 level is I am going to put some numbers in here. Iman mentions a really good question too, which I kind of hinted at with this on the bottom. Iman's question is, what if the products are all solid, or what if they're like a solid or a liquid or something like that? Well, that's a really interesting question. Let's make up a fake one. Let's say I had the chemical. This is totally fake, guys. I'm just making this up. Okay, so A goes to B plus C liquid. All right, just kind of make up a fake one. Well, what the heck? What would you do with this one, right? I mean, the solids don't count. So K is products over reactants. I can put the A there. Oof, my pen is not liking this slide, is it? Well, if none of the products are included, you just put a 1 there. And this is normal. Like this is totally could happen. I'm not saying it will happen. But it could, like it's a fair question. So to answer your question, Aman, and for anybody else who had that question, if the products are all solid or liquid and you don't use them, then you just put a 1 there and you go to your reactants. And that's kind of what I was hinting at the previous slide when I put a 1 there. Yeah, Abdullah and Abdul Halim, exactly. Wow, you guys are good. I'm impressed, I must say. It's too bad that we aren't doing this for real, on campus, and I'm not your lab instructor, but anyways. All right, give me 5 minutes or so. Well, I kind of hoped we would have finished this today, but I had some technical difficulties at the beginning. But I'd like to put some numbers into this situation. Oh, there's so many examples. And then I might end off on this slide. Like, what is the point of these numbers? All right. And okay, so let's take a minute. let's look at this. So as I mentioned just a minute ago, I'm going to take this up one more level of difficulty. We are just creating these formulas just like we did in the first section with rate laws, but what's the point of making a formula and doing nothing with it, right? We need to put in numbers. So this is a very easy example. Well, this is like not the best example, this first one, but I'll kind of go through it and then we'll look at a couple more. So let me read the top statement there. If you know the concentrations of each chemical at equilibrium, and obviously, guys, this is something that we would give you, you can calculate Kc. So example, this is a very easy example here. At equilibrium, the concentration of nitrogen is 0.25, hydrogen is 0.1, and ammonia is 0.15. NH3, where you don't have to name anything. So your first step in this question, step number 1, is to write the equilibrium equation. Now you'll notice that whoever wrote this down put a 1 there. You don't need to put the 1 there, but that's step 1. Step 2, put the numbers in from the question and solve it, and that's it. That's literally it. We have to give you the numbers. I mean, it's pretty straightforward. The only challenge here, and again, I'm speaking from someone with years and years of experience teaching this exact course, is if you can't do step 1, then you cannot do any of this question and you will get a 0. If you can do step 1, then the whole question is easy. It's a joke, full marks. And yeah, so like as Aman says, this is typically a 2-part question. Part number 1, find your equation. Part number 2, calculate the number. And again, the issue is if you can't do part 1, you are in trouble. Now, I've had students in the past get this equation wrong, but I still give them full marks in step 2. So I mean, I'm not going to give you guys a 0 if you forget like the 2 or something like that. I mean, it's not a big deal. You won't get full marks, but I don't give out zeros. Not normally. All right. I don't know what I want to do here. I don't feel I want us to like just go through. Oh, great question. Go through all of these right now because it is 10 after 5. I think I have an idea. The other question, and it's a perfect question because I didn't even think about answering this. There are no units for Kc. Nothing. No units. No units for K even, not even Kc. We'll learn more about other Ks in other units. There's Ks for Ka for acids, Ksp for solubility. There's so many Ks. If you guys think this is not important, it kind of is and it kind of isn't. For engineering and medical science students, this is extremely important. The equilibrium constant of acidity in blood is how you get someone with acidosis or alkalosis. So people who have their pH of their blood is changing, could be from hyperventilating or not breathing. It's based on Ka. People, engineering students here, if you're drilling offshore, you're drilling for oil, and the well bore, the hole in the ground where you're drilling to get oil, starts to become clogged with like solid particles like calcium, that's related to Ksp, and there's ways to use chemicals to clean it, to clean the well bore. Again, well bore meaning that hole that you drill. You guys probably know more about drilling than I do, but I do know that Ksp is very useful for engineers and Ka is very useful for medical science students. So you will see this. So guys, I have a plan because it is 10 after 5. I'm going to clear my writing here. Here's my plan. Okay. What I'm going to do is I would love, sorry guys, my computer's going a bit crazy here today. What I'm going to do is I would love for you guys to practice these 2 slides between now and Tuesday. And, maybe you're waiting for me to show up on Tuesday for class. You can just practice these. Now, what do I mean practice? I mean, the answer is right here. What I mean by practice is try to write the KC expression and see if you can get this exact number. You'll notice the scientific notation. So what I would like for you guys to do between now and Tuesday is to see, using your calculator, please try to not use your cell phone, but see if you can get these numbers. Okay, and this one as well. Okay, now this is where I want to end. What do these numbers mean when you calculate it? What is it even saying? And this is wink, wink, wink. This will be my finale of today. Very important, extremely important. What does the value of K mean? If the value of K is large, so if it's a really big number, meaning it's bigger than 1, could be 2,000, could be 30,000, could be 10 million. If the value of K is large, there are more products than reactants. Products are favored. If K is small, so less than 1. Now, I don't mean negative. You're never going to get a negative number here, but less than 1. So like decimal 0.0005, 1 times 10 to the negative 16, right? A very small number. There are more reactants than products, and reactants are favored. And I have a trick that I've never forgotten in my life to remember this. Okay, I want you to think of a chemical reaction. Okay, so if K is bigger than 1, it's products. If K is less than 1, it's reactants. Now, what's the trick there? The trick is, I'm getting a comment up there. Maybe somebody's writing it right now. I have a problem with I can't write on my slides and look at my notes at the same time. Look at where the arrows are pointing, or like the greater than or less than sign. So if K is bigger than 1, it's pointing at the products. If K is less than 1, it's pointing at the reactants. That is how I learned it when I was a young student, and I've never forgotten it because there's no reason I should have this in my memory, but I'll never forget it. So, if it's greater than 1, it's pointing at the products. Less than 1, it's pointing at the reactants. We will talk more about this on Tuesday. But that's going to become very important down the road. Okay. So 2 questions, and then halas, we're finished. You guys can go. So let me talk about Aman's questions first. First, yeah, I mentioned there's no units. Second, Aman said, do we need to show the steps? No. What I want to see is the formula and then the answer. So Aman's question is, do you need to show the steps? I can explain that just once my computer decides to go back a few slides. I don't know what's going on. I think I really honestly just need to restart it. So to answer Aman's questions, I just need to see these steps. Step 1, step 2, that's it. You could even skip step 2 and show me the answer, but I really need to see step 1. I need to see the formula and then the answer. The reason I say that, if you get the answer wrong, I can't give you part marks, because if I can't see the formula, I can't see any way to give you marks. So at minimum, I would write the formula and then the numbers, because again, if you get the formula right, but the numbers wrong, I can give you half of a mark. If you get the formula wrong, but the number right, meaning you put it into your formula, I can still give you half of a mark. The last question, and it was a good one, but I completely forgot. What if it equals 1? Great question. So if K is greater than 1, products. If K is less than 1, reactants. If K equals 1, then what that honestly means is the concentration of your products equal your reactants. They're equal. Well, yeah, no, I guess that's true. It's at equilibrium is what I should say. And the products aren't favored, the reactants aren't favored, they're equal. So greater than 1 products, less than 1 reactants. If it equals 1, which would be very rare, it would mean your products and your reactants are equal. Whew. All right, guys. I didn't mean to go this long, but I think I say that every day. So anyways, I'm done for now. We'll talk more about this on Tuesday. Don't worry, there's no test coming up. You don't have to worry about a test for a while. But we'll talk more about this on Tuesday, and maybe we can finish this chapter on Tuesday. We'll see. All right, guys, any questions? If not, have a good night. Wash your hands. Be safe. Take care out there. All right, cool. I'm going to go. Thank you very much, Abdul Rahman. Thank you, Yasmin, Abdul Halim, Abdullah. Thanks, everybody. Aman, I'm just saying, going back to who kind of commented. Thank you, everybody. Thanks, Harold. Have a good day. Take care. Be safe. I'll see you all on Tuesday.